Right, so we have combined translation and rotation. So I have a bicycle wheel. Just don't be distracted by all these pins that are sticking against the tires. These are just for marking the positions. So combined translation and rotation is something we have not done yet. We have done translation only for objects, going up and down inclined planes, going vertically, projectile motion. And for rotation, we have things that are rotating in place, such as a disc spinning, right? It could be accelerating or decelerating in the angular velocity, but they've been just spinning in place. So now we want to combine them. A very intuitive way to combine them is just the bicycle wheel. Everyone has seen bicycles, and if you don't know how to ride them, that's still okay. You know how the wheels work. So we have a bicycle wheel, and the bicycle wheel, if you think about this wheel, it translates forward as someone rides the bicycle, right? And at the same time, the bicycle wheel also rotates around its axle. So there are two combined motions for every part of the bicycle wheel, the translation and the rotation. So let me demonstrate. So here, this is the bicycle wheel. So the translation will take the whole wheel forward, just like that, right? So every part participates in this translational motion with the same exact velocity, the velocity of the center of mass. So let's put this down in translation. So V everywhere is the same as V center of mass, right? Everywhere. Alright, so translation is this. Rotation, on the other hand, let's try rotation. So let's do this. And here's a rotation. This is a very neat trick. Just rotate in place. I have to put two pins here because otherwise I'll be rotating around an axis of rotation that's not exactly axial. Something like this, you would probably not like this. It just goes up and down. Doesn't look like a bicycle wheel, right? So now we just saw rotation. And the rotation is every part participates equally only in the angular velocity, but not equally in the linear velocity. The rim moves with along a larger circle with a larger linear velocity, but everywhere else closer to the spoke moves around a smaller circle with a smaller linear velocity. So the participation is only equal with the rotational velocity, angular velocity, but not with translational velocity due to the rotation, right? So let's put this here, rotation. So everywhere is constant, same. I shouldn't have said constant, but it's same everywhere. On the other hand, the velocity is not the same. Velocity really depends on where you are at, so it's r times omega. This r depends on the location. So if you're only halfway along the spoke, then you're only tracing half the circle's circumference. So your linear velocity is half as much. So let's think about that as we combine the motion. And so here's one particular point in time. So this is the bicycle wheel. So the center is moving forward. So the center mass has a velocity v center mass. And let's just assume that the bicycle wheel is rolling without slipping. We're just riding the bicycle normally. So the condition would require this, right? So if you look at this, v equals r omega. So that seems to be the rolling without slipping condition. So let's do v equals r omega is rolling without slipping. What that gives us is the velocity as you're rotating across this axis rotation right here. Let me mark it here. Okay, so right here is axis of rotation. The reason I'm picking it here, I'll explain slightly later, but just imagine the whole wheel is kind of falling forward, right? So this point does not move instantaneously. So it falls forward, the whole wheel falls forward. So the V equals R omega applies to this point, the center mass, this point. And it is exactly 1 r away. So the center mass has to move at this speed that is related to the angular velocity. So this is actually center of mass. And if you use that idea, this point has to move at twice the center of mass velocity. Or you can say it's the combination of participating in its rotation. Here's translation, the V center of mass. Everything translates with that same speed, and then you also add another component because you're rotating around this point. So that is this other also equal to center mass. So if you look at it right here, the velocity scales. Velocity scales with how far away you are from this point, this axis rotation. So the top point with the blue pin moves twice as fast as the axle. So that's why it falls forward, and then it is basically going ahead of the axle in the next photo, right? So on the other hand, over here at the bottom participates. Let me change the color so we can see better. So the bottom participates in overall translation forward because it's part of the translation, right? And then it also rolls. So that rolling will actually kick the bottom backwards, and that is this direction of V center mass because it's a certain distance, r distance away. I don't think I drew it exactly the right lengths comparable to the other side. So let's draw it slightly longer. So these are exactly the same. So this part is due to the translation. This part is due to rotation, right? So translation wants to move everything forward, and rotation wants to move this point backward, exactly the same velocity. So what does that mean? This point is staying put, right? So what we call this axis rotation, that's really weird. The red dot just keeps going to the background. Okay, so now it stays. Okay, so this axis rotation, which is instantaneously at rest, we call this instantaneous axis rotation. So this is okay. So let's keep going with this other pin right here. So let's go back to black marker. So this pin participates in an overall translation forward, and also participates in the rotation that would rotate it downward. So it would be this way. They're the same exact magnitudes because we have already determined that. So the overall velocity will be in this direction. So this is the velocity of that pin, and it is going forward but also kind of downward. That will cause this pin to fall down and move forward, right? So the next diagram here, so the overall translation of the wheel will cause everything to move forward again, and the participation of the pin in rotation will rotate it downward, right? It's rolling. So the overall velocity, I think I should have drawn dashed lines in the other diagram. So the overall velocity is pointing further down, and the magnitude wise, this is actually, if I could draw a single line, this is actually the longest because the two velocities are adding straight, and this is slightly longer than the single velocity, but it's actually getting a little less because the two velocities are not exactly adding and in a straight line. And then this one is shorter, kind of shortest of the three. So you can see that besides the pin moving in different directions, initially at the top is moving directly forward with the maximum amount of velocity, and as it rolls forward it starts to point its velocity downward to make this motion down, and then it also reduces its velocity magnitude. it reduces magnitude a point further down, and as it gets to this point, so sometime later it gets to this point, and we have the exact same condition as this red condition here. So let's go back to the red pen, so that the rotation will cause this to be kicked backward, and translation overall of everything will cause it to move forward, and the slashes are the same. This is only relevant to this diagram. The slashes, red slashes, are not the same as these black slashes. So now the velocity has gradually and eventually reduced to 0. So every point on the rim or anywhere else other than the center of mass is moving with this relatively complicated fashion. It accelerates, decelerates, accelerates from rest as it gets picked up from the back side of the wheel, and accelerates as it changes velocity, magnitude, and direction. As it gets to the top, it gets to the maximum amount of velocity, and it moves forward, and then it starts to accelerate negatively, and basically reducing its magnitude of velocity, and also points further down and down and down, reducing the velocity until it gets to 0. So everywhere it does the same thing, except for the center of mass, which does exactly the same thing, exactly the same thing, exactly the same thing. Okay, so once again, the combination of translation and rotation will cause the rolling to happen. And the pure rolling is rolling without slipping, so that the translation and rotation will be locked in this exact fashion. But what if you have something that is not exactly pure rolling? Say it's rotating faster. Say if it's V center of mass is less than R omega. So this is actually rotating faster than it is translating. So I would imagine it'll try to roll and down something like this. This is the trace of the top pin. It'll do this. And if you have center mass, if you're translating faster than you're rotating, so that means the bottom is never going to be a 0 velocity. So you do something like just do this. But if you have center mass velocity the same as this R omega, so you'll just basically go and come to a stop, and then go again, come to a stop, and go again, come to a stop. And of course, if you could also have some different situation where you're actually moving forward and you're rolling backwards, such as this. So this V center of mass is greater than 0, and omega, and in this case is I would say it's also greater than 0. Greater than 0 means it is counterclockwise. So you're moving to the right, you're spinning backwards. So you'll be like doing this on the rim. So next time you do though, you may imagine, oh, this is actually just kind of a combination of a translation and rotation. Actually, this is the same thing. If you think about how your pen is moving, so this way here, this way means a backward rotation, right? And as you are moving your overall hand to the right, you're making this doodle, woo, just like that. Same thing happens with the wheel if your wheel is rotating backward as you translate forward. And back over here, as you're rolling forward, see that? This motion of your hand moving forward, and you're also moving overall your hand to the right. So that just kind of makes this, right? So next time you doodle, imagine this is just practicing physics. Thank you.